Growth and decay. Well, you kind of look a little bit of growth in GCSE when you talk about compound interest with percentages. Because when you talk about compound interest at GCSE, what you talk about is a question like this first example where you're investing so much money into a bank and you want to find out how much money you make at the end of so many years when it goes up by a certain percentage each year. And what you did was you took your original amount and you multiplied it by the percentage increase and then put it to the power of how many years that you were talking about. And that is to do with growth and decay and is actually an example of a geometric sequence. So if we have a look at this example here, we're told that Andy invests £M at a rate of interest of 6% per annum. 6% per annum means 6% per year. After 6 years, it is worth £15,000. How much to the nearest penny will it be worth after 10 years? Now, what must have happened here is we've got to get the price after 6 years is you must have had his original amount M and you must have times it by a 6% increase per year. Now remember, a 6% increase means your original 100% M added on 6%, which is 106%, which is 1.06, and you've got to raise that to the power of how many years it's happening for, so it's 6 years. Now that is equal to £15,000. So to find the original amount, you must do that £15,000 divided by the 1.06 to the power of 6, where M is equal to 10,574 pounds and 41p if you were to round it. But to keep the accuracy as best you can, I would at this stage just write it down to a few decimal places. Now, this means in this geometric sequence, which it pretty much is, we've got a common ratio here which we're multiplying by every time, which is the 1.06. So if we're to write this as a geometric sequence, we could say that the common ratio is 1.06. We now know the value of the first term because we just found it as £10,574 and 41 if we're to round. Now what we're asked to find the value after 10 years to the nearest penny. So now we've got our original value and we know that the common ratio is 1.06. We're going to put it to the power of 10 years. So 10,574.41 times by 1.06 to the power of 10, and that gives us £18,937 and 15 pence. Now the only thing you have to be a little bit careful of here is that it isn't strictly a geometric sequence, because that 10th year is actually the value at the beginning of the 11th year. Because what we are actually told at the start of the question is we're told the amount at the start of the first year. Okay, so when we're talking about these values here, this one as well, that actually represents the price at the beginning of the 7th year. So it's not strictly written as a geometric sequence, but it is sort of following the pattern. So just be careful that it actually represents the value at the beginning of the 7th year. And the reason why we have to be careful is because we're told the price at the beginning here of the first year rather than the price at the end of the first year. Now, there's also another question to look at. What is the first term in a geometric progression which goes 4, 8, 16, 32, which exceeds 1 million. Now, the first thing we need to do here is we need to find out what is the common ratio. So what is the common value that gets us from 4 to 8 and then from 8 to 16? Well, obviously you're timesing by 2, because 8 divided by 4 is equal to 2. Now, we know what the first term is because it is 4, so we want to label that. And remember, we're looking for the first term to exceed £1 million. So we're looking for the first term that is greater than 1 million. So, the general rule for finding the nth term of a geometric sequence, remember, is the first term times by the common ratio to the power of n minus 1. So, if we substitute what we know into this equation, we know that a is 4, and we're timesing that by the 2 to the power of n minus 1. Now at this stage, I'm going to divide both sides by the number 4. So what we're going to have is 2 to the power of n minus 1 is greater than 250,000. Now, the only way we can solve this problem is, because we're involving 2 to the power of something, is, remember, we've learnt about logs, we're going to take logs to the base 10 of both sides. So log to the base 10 of 2n minus 1 and log to the base 10 of 250,000. Now, remember the power law from logs, where we bring the power n minus 1 down to in front of the logs. So we're going to have n minus 1 times log of 10 to the base 10 of 2 is equal to log to the base 10 of the number 250,000. Now, remember, we're trying to get a situation where we've got n on its own, so we need to split this log up here into its two parts, which is going to be n times log to the base 10 of 2 minus log to the base 10 of 2, and that's greatest to still the same value. Now, we want to be in a situation, obviously, to solve this where we've got n on its own. So we're going to add this to both sides. So we're going to be left with just log times n times log to the base 10 of 2, and that's greater to than this, plus what we brought across. Now, if you wanted to, you could combine this, remember, and put it as one logarithm, because the addition law means that we multiply these two numbers together. So, the final thing to do is divide by the common value log to the base 10 of 2 to leave n on its own. So then we're going to be left with this, and if we type this into a calculator, when we've got it all, we should come out with a nice number, which is this is greater than 18.93. Now remember, we're looking for the first number that exceeds £1 million. So if we had the 18th number, it would be still just under. We'd be just under the 1 million mark. So we must be looking at n as being a minimum of 19 to exceed 1 million. So the first term to give a number that's above 1 million will be the 19th term in the sequence.